can hear you.
I guess I was not being heard. It just got unmuted now. So, so hybrid storage systems combine different storage devices with various varying characteristics. Um, so it can be a fast device with lower latencies and lower capacities, and a slow device with slightly higher latencies and higher capacity. So we combine these different devices to achieve high performance and high capacity at low cost. So in a hybrid storage system, we have three functions that are very critical. The main function is to place the data in one of these devices when the applications send IO requests to the system. So the problem with prior approaches that perform data placement is they lack the adaptivity to changes in the workload. So if the workload changes, the policy remains the same and they don't really adapt to those changes. And then if the device types change and the configurations change, then these policies don't really perform so well. And these prior data placement techniques also lack the extensibility to more devices. So if you increase the number of devices in a hybrid storage system, you need to uh, re-engineer or redesign a new policy altogether. So, so the goal of this work was to design a data placement technique that provides both adaptivity and extensibility. With adaptivity, we continuously want to learn and adapt to changes in the workload and device characteristics. And we also want to have a data placement technique that can be easily extended to any number of devices in the storage system. So to this end, we propose Sibyl, the first RL-based data placement technique for hybrid storage system. As I mentioned, provides adaptivity, extensibility, and also it provides ease of design and implementation, and the computation overhead is very minimal. So some of the key results, we evaluate Sibyl on real systems using a wide range of workloads, and Sibyl improves performance by 21.6% on average compared to the best performing prior data placement technique in a HSS configuration with 2 devices. And we also see on a HSS with 3 devices, Sibyl outperforms the state-of-the-art policy by 48.2%. And we have an Oracle policy that is kind of a reference for us for evaluating the accuracy, and that's the upper end of our evaluation. And Sibyl achieves 80% of the performance of an Oracle, and the storage overhead is around 125 kilobytes. So and also Sibyl is completely open source, so you can look at this GitHub repository and start exploring the code. So in today's talk, I'll briefly I'll start with discussing the shortcomings of prior data placement techniques, and then we look at how we can formulate data placement as an RL problem, and so on. So let me see. There's some chat. Okay. So so before we go to the problems or limitations of prior data placement techniques, we start with some introduction on what is a hybrid storage system. So in a hybrid storage system, you have multiple devices of varying characteristics. A fast device, which has very low latencies, and a bigger slow device, which is having a very high read and write latencies. So there is also a storage management layer that is implemented in the operating system that exposes a unified logical address space, which combines the capacities of these two devices, and it allows the application to basically place the data in these devices. So the main responsibility of this storage management layer is to uh, take the reads and writes that the application sends, and then determine where the data has to be placed and where the data has to be read from. So this has all the brains to decide, okay, I need to put the data in the fast device for this IO request, or in the slow device. So it basically determines where the data should go. And there is also a promotion and eviction policy, which is not happening when there are IO requests that come from the application. But this is very essential to make space in the fast device for new data. And also basically when some data becomes very hot or is accessed more frequently, you need to move the data to the fast device so that you get a higher performance. So so the performance of a hybrid storage system highly depends on the storage management layer's ability to manage these diverse workloads and also these devices. So with this background, we'll look at the key shortcomings in prior techniques. So we observe two key shortcomings that significantly limit the performance benefits of prior techniques. The first one, as I mentioned, is lack of adaptivity to changes in the workload and also changes in device types and configuration. And the other limitation is lack of extensibility, which means that you need to design a new policy if the number of devices in the system decreases or increases. So we look at lack of adaptivity, and I'll show some empirical results here. So here we see normalized average request latency on the y-axis, and this is basically the average request latency normalized to a policy which is fast only, which means that you place all the data that is coming from the applications in the fast device, and that's the best policy that we can, and that's an ideal policy that we normalize it to. And we look at three baselines in this case, or three prior approaches. CD is a heuristic approach which places all the data in the fast device, and when the fast device capacity is fully utilized, it moves the data to the slow device. So what data is moved to the slow device is based purely on a least recently used kind of mapping policy. Then we look at RNN HSS, which is a recurrent neural network based data placement policy, which is supervised learning approach, where you train a RNN model and then that predicts the access frequencies for an epoch, and then we place the data based on that. Then there is the Oracle policy, as I mentioned, which has complete knowledge of future access patterns. So we compare these two policies, and we see that in some of the workloads that you see in the y-axis, the difference between the CDE and Oracle is varying significantly across different workloads. So you can see that in HM1, the difference is not so much, is slightly less, but compared to PRN1. So a policy which is based on heuristic or supervised learning technique will not adapt to these changes in the workload. So let's look at changes in device types and configurations. So these policies do not consider underlying storage device characteristics like changes in the difference between the latencies in the devices, and also doesn't look at what is going on underneath in the devices like garbage collection or some of the other maintenance policies that these devices have. So we again look at we look at two configurations here. So HSS configuration one and another configuration, and we still see the normalized average request latency in the y-axis. So here we also add another policy which is slow only, which means that all the data that comes from the application is being placed on the slowest device. So when we look at this data, we see that in the first configuration, the CD policy is actually performing worse than the slow only policy. You can see it in two of the workloads, HM1 and PRN1. And this is because the Sibyl has CDE has a very fixed policy, a very fixed placement policy, which is place all the data in the fast device and then move it to the slow device and it reaches 100%. And this actually causes a lot of evictions or migrations between the two devices. So this is with one configuration, and if you look at the other configuration, it actually performs uh, slightly better than the slow only policy, because if you place all the data in the slow only policy in this configuration, where then the latency would obviously be higher. So you can see that the policies are giving different results when you run it on different configurations. So we then move on to lack of extensibility. So these techniques are very rigid and they require significant effort to accommodate more than two devices, or even if there are multiple devices, if you remove a device, then it needs an entirely new policy. So when you increase the number of devices from a dual HSS to tri HSS, we design a new policy. We need to design a new policy. Uh, I'll give you an example. So when you want to move the data from, when you take CD as an example, and when you want to move data from the fast device to the slow device, at some point you need to determine where do you want to evict this data, whether to evict to the middle device or the slowest device. So these kind of challenges arise when you take these prior approaches and try to extend them. So our goal in this work is to design a data placement mechanism that can provide both adaptivity, adaptivity by continuously learning and adapting to the application and underlying device characteristics, and also extensibility to number of devices in the HSS. So to this end, we propose Sibyl, which formulates data placement as an online reinforcement learning problem in hybrid storage systems. So this is a brief discussion on the limitations of prior approaches. Do you have any questions at this point? I guess not. So we'll move to formulating the data placement technique as a reinforcement learning problem. So we first start with looking at some basics of reinforcement learning. In a reinforcement learning framework, we have an agent, which is and an environment. So the agent looks at the state of the environment by looking at multiple input features, and then it performs an action, and the action affects the environment. So the environment then gives a reward based on the action of the agent. And typically the reward happens in the next time step uh, after the action. So this is a brief description of the RL framework. So the agent learns to take an action in a given state to maximize the numerical reward. So the whole idea of RL is to have a good policy, which is let's say you can describe it as a function which maps the actions to the action value function, and that we typically call as q value function. So that is something that we always try to maximize. So we look at how do we map Sibyl to this kind of a framework. So instead of an agent, we have Sibyl. And the environment is the hybrid storage system, and the state is basically represented by features of the current request and also the system. And then the action is to select a storage device to place the current page. So by current page, we mean the incoming IO requests page. And then the reward is basically the request is a function of the request latency of the last served request. So this is how we formulate the data placement policy as an RL problem. Now we look at what is the state. So state is basically a snapshot of the environment, and we choose a limited number of state features after performing a lot of empirical analysis of different features, and we basically have six-dimensional vector of state features. And here you can see the different features are the size of the request, the type of the request, whether it's a read or write, the access interval, which is if you look at two accesses for the same page, you can count the number of accesses in between, and that is the access interval. Then you have the access frequency, and then the capacity of the fast device, and then the current location where the page is already placed. And we basically reduce the implementation overhead by quantizing the state representation into different bins. And here by bins, we mean we basically represent all these features as in terms of different size classes. So we trade off some precision to achieve this reduced storage overhead. And we also, from our empirical analysis, we see that RL agent is more sensitive to reward in this case. So I'll briefly discuss the reward next. So the reward is what is defining the objective of Sibyl. So if we want to improve performance, then basically we need to define a reward structure which takes into account the performance of the system. And we formulate the reward as a function of the request latency. So what we do is the reward is basically inversely proportional to the latency of the request. So which means that if the request is placed if the data is placed in the fast device, then the request latency will be low, and then the reward would be higher. And it's the inverse in case of placing it in the slow device. So what this reward structure encapsulates is basically the internal state of the device, which means that if there is some garbage collection going on, or if there are queuing delays within the devices, then this gets captured in the request latency. And it also takes into account the evictions that happen as part of the placement. So we have more details in the paper on how we also looked at other metrics for the reward structure or other scenarios, and we basically narrowed down on the request latency. So then we finally look at the action, and so the action is to place the data for every incoming IO request in one of the devices in the hybrid storage system. And that's a very simple action. So you can easily extend this to a number of storage devices, and I'll briefly explain how we can do that in the later in this presentation. And so Sibyl also does some kind of an eviction, has an eviction policy where once the fast device utilization is 100%, it moves the data, cold data from the fast device to the slow device. And it can also promote a page when there is an update from the application. So this is a brief description of how we formulate data placement as an RL problem. Now, I'll move to the design of Sibyl. And before that, if anyone has any questions, then I'll be happy to answer. Yeah.
So the last one that you had, so how does it choose the one with the page?
Sorry, can you be a bit louder?
The third point says that this the page is selected and the site. There's like the system respond. Or
I still don't hear you. So when
his question is how do you select the page?
so yeah, so even in Sibyl, it basically has a heuristic approach where it selects the page based on the access frequency, and it looks at the pages with the lowest access frequency, and then which is least recently used or the least used pages, and then it moves those pages to the slow device. So that's a problem that I would discuss much later in the presentation, which is these policies also need to be adaptive for having a good performance, for getting a good performance. So if we have a fixed policy which looks at only some characteristics, then that will also be that also limits the performance to some extent. So I'll discuss the design of Sibyl. So Sibyl has so there are two threads in the design of Sibyl. So one thread is called the decision thread, which takes the input request or the storage request and also looks at the environment, and it basically decides where the data should be placed. That is the decision thread. Now we also have a training thread. So the training thread is basically uh, the thread which actually takes the state, reward, and action information. We call that as experience in Sibyl. So this combination of state, reward, and action, and it uses that to train the neural network. So in Sibyl, what we use is a simple feed-forward network with one input layer, two hidden layers, and an output layer. So it's a simple network. And this RL training thread is basically training that neural network in an asynchronous manner, and it periodically updates the weights, policy weights to the decision thread. So the decision thread continues to make the decisions for the incoming request, and the training thread getting trained is doing the training in the background, and the policy is updated frequently so that the training overhead or the latency of training is not on the incoming request. So if you have to train the network and then perform the inference, then it adds a significant overhead on the incoming IO request. So as I said, this is asynchronous execution. So this is the design of overview of Sibyl. So the box in the bottom is the decision thread, and the one at the top is the training thread. So I'll start with the decision thread. So you receive. Let me use. So the incoming storage request is and the state of the environment is basically seen by the observation is taken by the decision thread, and uh, translates that to an observation vector, and that is the state for the inference network. So inference network is also a simple feed forward network with the same design as the training network. And this inference network would make a decision which actually maximizes the Q value for Sibyl. And then the action is, as we discussed, is to place the data in one of the devices, either in the fast device or in the slow device. So this is after the action is performed, then the hybrid storage system has to issue a reward to the agent, and this is to convey to the agent whether the placement decision was improved the performance of the system or not. And once the reward has been issued, the state, action, and reward is collected as experiences, and then we store that in an experience buffer. So this experience buffer is like a simple buffer that stores all these experiences from the incoming requests, and then this is typically stored in the host DRAM. So this is from the experience buffer. The training thread picks up these experiences in terms of batches, and then that would be the training set for the training network, and this happens frequently. So once the training network is the convergence happens, then the policy weights or the training weights of the training network are passed on to the inference network, so that it actually can adapt to these weights get updated, and it can adapt to the changes in the workload. So this is a very brief overview of the design of the two threads, and this basically is what Sibyl looks like. So any questions on this? Yes.
How large is the buffer in those two?
So this is again something that we had to empirically determine how many experiences to store, and we kind of found out that if we store 1,000 requests or 1,000 experiences, that gives an ideal performance. But more than that would still give you slightly better performance, but at a cost of storage. So 1,000 experiences is what we store currently in the experience buffer.
In the training track, does the data from the buffer override the existing data, or does it get added?
Yeah, it gets added.
So there's more and more data.
Yes.
Is there like a limit, or is it just overload this too much?
So the training happens in batches. So what happens is when you are training with a batch of with 8 batches of 128 samples, then you would keep updating the experience buffer, and then it continuously keeps updating the training network's weights also during the training. So you keep I mean, it's a constant process that happens.
So for example, when you run the system and then you switch to like a different kind of job in the middle, would it make sense to like have focus more on like newer experiences than on the old ones which were from the different job?
That's a very good question. So yeah, that's okay. I'll try to explain it this way. So if you are looking at experiences from, let's say, newer workload and from an older workload, then the time for convergence or the policy to take the right decisions would be slow if the access patterns change. But again, it depends on the workload. So it may be slower, and it may make decisions which are not ideal at that point. But overall, I mean, in the span of the entire workload, you can actually see better results. Yeah, as you go on. So yeah, I agree with you. Yeah.
Yeah, I guess if you switch from one workload to another, we converge quite quickly to the best solution of the second one, right?
It depends on how many experiences are there from the first workload.
Let's say, quite large experiences. Let's say we have two parallel clusters, like extensible workload as its whole decision making of whether it goes in the fast or the slow.
Yeah.
I guess that there are also other major problems associated with it.
Yes, that's actually, I mean, that's a good question. So, which workload is more dominant when you're running parallel workloads is a question that we need to, I mean, we actually do that experiment in the paper and we see that for mixed workloads where you parallelly run multiple workloads, you see still a better result compared to these heuristic approaches. It's always, I mean, when you take the prior approaches as a reference, you still perform well, but we're still not sure whether that's the ideal performance that we can expect. So, so that's more or less what how we designed Sibyl, and now I'll jump to the evaluation. So we evaluated Sibyl on a real system with multiple HSS configurations, and as I mentioned, dual hybrid and tri-hybrid systems with 2 and 3 devices respectively. So this is an example system where we have 4 devices. We have a high-end Intel Optane device, which is the fast device. We have an Intel TLC SSD, and then the A-data low-end SSD, and then a hard disk drive. So these are some devices that we use to make a hybrid storage system, and all the training and inference is happening on the CPU itself. So we evaluate with two in a HSS with 2 devices. We actually have 2 variants. One is cost-oriented HSS configuration where we have the high-end SSD and then a low-end hard disk drive, and then a performance-oriented HSS configuration where the latencies of the 2 devices are more comparable. So you have a high-end SSD and a middle-end SSD. And we also choose 18 different workloads from MSR Cambridge suite and FileBench suites. And we also we evaluate 4 prior state-of-the-art approaches, CDE and HPS, which are heuristic based. And here we mostly look at let's say access frequency as the main metric, and then based on that we make decisions on where to place the data. Then we have archivist and RNN HSS, which are the supervised learning based approaches. Archivist is a classifier based approach, and then RNN HSS is, as I already mentioned, is based on recurrent neural networks. So on a performance optimized, cost optimized HSS configuration, we see that here again we show the normalized average request latency, and Sibyl is shown in this brown color, maybe pink, red. Okay, so you can see that across all the workloads, Sibyl performs well compared to the prior approaches, and it's also in some of the places you can see that the difference between the Oracle and Sibyl is not so much. So it consistently outperforms all the baselines. On a performance-oriented HSS configuration, we see that Sibyl provides 21.6% improvement, and it achieves this by dynamically adapting its data placement policy. And it also achieves 80% of the performance of an Oracle policy, which has complete knowledge of future access patterns. So we then look at the performance of Sibyl on a tri-hybrid storage system. And here, how do we, so Sibyl was extended to 3 devices. And how did we do that is we added a new action to the RL agent, which means that we need to add another node in the output layer. And we also need to add the remaining capacity of the new device as a state feature. So these are the two things that we need to add for extending the policy for two devices to 3 devices. So this is the configuration that we use in tri-hybrid storage system, high-end SSD, mid-end, middle-end SSD, and a low-end HDD. So here we also had to extend the prior approach for multiple devices, which took significant effort in redesigning it. And we took CDE as an example and extended that. So compared to CDE, Sibyl for tri-hybrid system outperforms the CDE policy by 48.2%. And it also reduces the system architect's burden by providing the ease of extensibility. So now coming to the overhead of implementing Sibyl. So the total storage cost of the experience buffer and implementing the inference and the training networks for Sibyl comes to around 125 kilobytes. But there is actually a significant cost in tracking the metadata or tracking the features for each page. And for each page, we store a 40-bit metadata for the Sibyl to keep track of the access frequency, the request type, and so on. Because of the simple niche design of the network, the neural network, we see that the inference latency is around 10 nanoseconds, which is significantly lower than the access latencies of even the high-end devices. And then the training latency is around 2 microseconds. But since it happens completely in the background, it doesn't really affect the critical path. So we have a lot more results in the paper. We have the throughput evaluation, evaluation on unseen workloads. So this is an important result experiment that we did where we trained or we basically changed the access patterns very frequently. So we basically filled the experience buffer with one set of workload, one access pattern, and then change the access pattern so that we can understand how Sibyl makes these decisions. And we still see that Sibyl can adapt its policy for this kind of a dynamic environment. And then we also have mixed workloads where we run parallel workloads in parallel, and then that also adds a lot of dynamic nature to the environment. So we also evaluate using different features and basically decide on the most important features for the observation vector. And we also show the different hyperparameter values. That so we basically do a sensitivity study for the hyperparameter values and show that the chosen values are giving the best performance. And also to the fast storage capacity. So if we vary the fast storage capacity to different sizes, then how does Sibyl adapt its policy? So that's another experiment that we did. Finally, I think the most important part is to explain these decisions of a reinforcement learning agent. And we try to do that in the paper, and I would recommend going through that section. So here's the link to the paper and also the link to the GitHub repo. So I'll quickly, before I conclude, if you have any questions, I'll be happy to answer. Yes, please.
In one of the first slides, I think you also showed another neural network that tried to do basically a similar, kind of similar solution, right?
Yes.
I assume that the difference between Sim and this neural network would be it's like lightweight, you could probably say. So we don't have like there's a set of 40 bits overhead for each agent store. But if I'm not remembering wrongly, you also showed that this neural network performs worse than regarding like placement of the actual pages. Why is that?
So no, that the prior approach, if you're talking about the prior approach, that's a different design altogether. So that uses this technique, which trains the neural network offline based on let's say access frequency as the metric, and then it deploys the model to determine the access frequencies of the pages that are coming from the system. So it's an offline approach which is trained on using labels. But on the contrary, Sibyl is completely online, so it doesn't have any understanding of the system before it starts.
I might have missed it.
Yeah. Okay. So, any other questions? So I'll quickly conclude. So we introduced Sibyl, which is the first RL agent, RL-based data placement technique in hybrid storage systems that provides adaptivity, extensibility, and ease of design and implementation. And we evaluate Sibyl on real systems with different workloads, and Sibyl improves performance by 21.6% compared to the best performing prior approach on a HSS with 2 devices. On HSS with 3 devices, Sibyl outperforms the state-of-the-art data placement policy by 48.2%. It also achieves 80% of the Oracle's performance with a small storage overhead. So that concludes the discussion, the summary of the paper, and now I'll move to critical analysis. But before that, if you have any comments on how to improve Sibyl, or if you have any questions, I'll be happy to answer. Yes, please.
Could you maybe explain a little bit the quantization of the space of the state space?
Yeah, okay. So let me see if I have a backup slide on that. No, that's so. So this is basically what I meant when I said we quantize the state representation. So we define this number of bins in which we store these features. So size of the incoming request can only go in 8 bins. So you have a bin for 512 bytes, 1 kilobyte, 4 kilobytes, and so on. So you have 8 such bins. So you basically do some approximation to reduce the number of bits that you use for storing these features. Similarly, you have type of incoming request is just using 2 bins because you either have a read or a write. Then you have access interval, which can be stored in 64 bins. Similarly, access frequency and current page placement can be either in the fast device or in the slow device. So this is what we try to reduce the size of the number of bits that we use to represent these features, because as I said, each page can take up to 40 bits. So we need to kind of reduce the size of this representation. Okay. Yeah. Nice.
Yeah, just you said that it's the best option that we can use. Does it also consider let's say, load into a fast and the fast is clean, if I load it into the DRAM or if I actually write it to the underlying that structure?
So what we are looking at is we don't go to that level of these devices. So what we are looking at is whether the data is already available in the fast device or in the slow device. So the Oracle basically makes the data already available in the fast device before the request can access the page.
Yeah, because I just want to know, I assume there's a lot you could do in that, also going more fine-grained, like including host DRAM and there's this DRAM, for example, and stuff. But I guess in current way this is implemented, it would lead to a lower complexity, I assume. Right?
That's very true. So yeah, we can actually go to the level of controlling whether the data is in the host DRAM within the SSD and then access from there. But we are working at an abstraction level which is much higher. So I think yeah, but I should also say that the implementation is of Oracle is also a very subjective thing, because we don't have a clear Oracle like the Beladi's min policy for caches. So the Belady selection policy. But in this case, we need to take into account the let's say the migration of the pages, the sizes of the fast device capacity and things like that. So this is a Oracle policy that was proposed in one of the prior approaches and prior in a prior work in HPCA 2015, if I'm not wrong. So yeah, but yeah, that's also an ongoing area of research to define the right oracle. Okay, so I'll move to the critical analysis. So let me start with the strengths. So the strength of this of Sibyl is that it's the first work to use RL for data placement in hybrid storage systems. And we evaluate Sibyl on real HSS configurations, which is not typically the case with prior approaches because they generally do it on simulators or show it on limited number of devices. Sibyl is also open source, so it hopefully enables future research on ML-based techniques in hybrid storage systems. And explainability of these RL-based agents decisions is a very critical thing. It's critical for understanding whether these kind of data-driven approaches um, are important for these kind of problems, or can we use these approaches for these problems. So we try to explain these decisions for different workloads and different configurations in this work, and I think that is one of the strengths of this work. So again, we show the extensibility to number of configurations. So that's another thing that designers don't have to spend too much time on redesigning these policies. Any feedback or comments on this? Yes, please.
Just, I'm surprised because you say Sibyl's actions are explainable. I would have assumed that we're simply looking at the placement, like decisions of Sibyl. I would very often not understand why it chooses to do the placement and say slower and faster ones, because it just sees the level of complexity I cannot understand. But apparently this is not the case, you say.
I mean, I kind of agree with you that what we are also trying to do here is to just have an interpretation of these actions and based on observations mostly. So, for example, what we see here is that if the difference between the two devices is, the latency difference between the two devices is very large, then Sibyl always tries to place the data in the fast device, because placing it in the slow device will incur a lot of latency. But if the difference between the two devices is reasonably similar, then Sibyl can understand, okay, this we only need to perform, only need to place the most critical data in the fast device. The rest can go to the slow device, because the access latencies are still similar. So that is something which we observed during our experiments.
Okay, so if I understand correctly, if the two devices are different, Sibyl converges to a kind of eager solution of trying to put everything in the fast device, which all in all is not good. So it performs worse on devices that differ more. Does this make sense? Because probably that you could also, like, this is just an assumption.
No, I'm saying the other way around.
You're saying the other way around.
So if the two devices are very similar in nature, the access latencies of them. So what Sibyl looks at is to place only the performance critical data in the fast device. And what Sibyl thinks as perhaps cold data can go to the slow device anyway, because
Yeah, but I just said, if the one device is very, very quick and the one device is very, very slow, you said it tries to put everything into the fast device, but that's not probably the optimal way to solve it, or to look at it, is it? Or maybe it is just the best placement.
Yeah, I mean that the actions can be. I mean, we can debate on those actions, because it also means that it thinks that the applications would access the data more in the near future, and it needs to be in the fast device rather than going to the slow device.
Yeah,
but in terms of like the fast device's ability to hold all the data, it may not be the case.
Yeah, but we can also argue for the argument for eviction from the fast device to slow device is not as expensive as not loading it into fast device or something like that. There are many reasons why it's okay.
You said it's not as expensive.
Yeah, I mean, you said it prefers loading it into the fast device. There could be many reasons for that.
Yes. Yeah, I mean, the migration is something that can also affect the decisions. So I think I'm running out of time, but I'll quickly go through the weaknesses. So one weakness is that Sibyl does not consider other optimization objectives, such as energy efficiency or lifetime of the devices. We just discussed one case where if you try to exploit the fast device more and more, then it also perhaps loses its endurance much faster. Sibyl's promotion and eviction policies are less adaptive to changes in the workload access patterns and HSS conditions. So I mean, to be fair to Sibyl, it's also not its job to kind of handle these things, because data placement is a very, very critical part of the IO request handling. So it needs to do that action well, and promotion and eviction have to be handled, but the way it's handling now, it's not very adaptive, because it still looks at access frequency and then evicts the data based on what is called in the fast device, or promotes the data based on the access frequency. So Sibyl also stores metadata for each page, and if there are millions or billions of pages, then it adds a significant overhead to the storage overhead to the system. And then this is me being somewhat overcritical about Sibyl. The hyperparameters were tuned based on the workloads that were chosen. And so this is an offline process that we used for tuning the hyperparameters. And this may not actually work when you change the workloads to a completely different set of workloads. And you may need to also tune the hyperparameters at that point. But there are some newer works in the machine learning domain which look at online tuning of these hyperparameters also, which can be adopted for improving this. On the storage, on the metadata aspect, I can also say that we looked at flushing some of the metadata to the one of the devices, one of the storage devices, and not maintain it everything in the DRAM. So that reduces some of the overhead, but then it also means that you lose some accuracy because you can't have all the data ready, and then you need to fetch the data from the backend. So that's these are some weaknesses that I could think of. But if you have some more, please feel free to add. Okay. So go with some discussion points, and so the first one that I want to discuss with you guys is how do we simultaneously optimize these multiple objectives? Right now, Sibyl looks at performance, but how do we optimize energy efficiency, lifetime of the HSS, of the storage devices? Do you have any ideas or comments on this? Yes.
I mean, this is a very similar question to simple multi-object optimization or whatever it's called. I mean, it's there are multiple probably solutions for that, but I mean, first of all, the assigning true weight, for example, for what you want to do this work for performance, energy efficiency, let's say lifetime, and then optimizing like a linear combination of these two, or how we calculate, or another way you try it. For these, there's probably multiple Pareto optimal solutions that you try to aim for. So this is a lot of probably has to do with planning before actually doing the project, what you're also aiming for.
And that's very true. So it's like we should say very experiment intensive. Um, yeah, something like that. But yeah, how do we, for example, if you think of energy efficiency, or what would you add as part of the input features of the reward? What would make the most difference? Or let's say if you want to optimize for lifetime.
Yeah, I mean, I guess when you have, and currently we have as a feedback only the latency, right? That we have for a page. I mean, there are multiple parameters you can add. For example, how much energy it takes for you to load from the fast device or from the slow device. You could also say, okay, beforehand analysis has shown that requests to this device very heavily decrease the lifetime of this device, for example, which is I think case with a lot of SSPs and stuff. So you can play with like parameters of the rewards and also the basically feedback.
Yeah, that's more or less what I was also thinking. Actually, the interesting aspect is that if you try to optimize some of these objectives, or at least one of these objectives, then the other objective may not get optimized so well. It can create suboptimal results for the other one. So just give you an example. So if you try to optimize for performance, then the best way is to look at using the fast device, like a cache, serving everything from the fast device. But that reduces the lifetime of the device, which is something that we are also trying to concurrently optimize for. So it's a challenge in terms of like finding a balance in when optimizing all these things. As you said, there could be multiple techniques or multiple models that can be used. And
I mean, this also introduces more challenges in hyperparameter training, right? For example,
exactly.
if we again introduce more stuff, it could be that at the end we simply converge to all we want a high lifetime, so we don't everything in the slow hyperparameter. So it's like another context.
So yeah, so multi-objective optimization is a hard problem. So there is, I don't have a clear solution at this point, but it's something that, as you say, is heavily dependent on the way you perform these experiments, how you can tune these policies, and so on. So, I mean, going by what we observed in Sibyl, I think the reward function was more important in terms of affecting the policy of the RL agent. And I guess we can come up with a more holistic reward function that takes into account the IO request latency, the energy consumption numbers for the writes and reads, and also look at the migrations or the evictions that are performed, and then also look at the number of writes that is performed on each storage device, and that perhaps can try to optimize for the endurance. But how do we combine all these things? That's the major trick here. And yeah, I don't have a good solution of this, but but there's something which is important for improving all these aspects. I think if we leave one and then if we try to optimize one, the other two is left behind. So this is a challenge that can be addressed to some extent by designing a good reward function, which looks at all these aspects, and perhaps that's one of the first steps.
This is just out of curiosity. Have you ever tried to sweep for good reward functions? For example, like genetic programming, probably from best data or something similar to that.
No, in this work we did not, but that's something which we are interested in. In this work, I would say we try to look at hit rate.
Yeah, not for this work specifically, but
yeah,
for more general.
Yes, actually, that's something which we want to try in some of the upcoming works that we have in this direction. Yeah, I don't have any good research answers at this point, but yeah, we also tried hit rate. As I said, we looked at uh, giving different penalties for the number of evictions that is performed and so on. But yeah, ultimately the reward is also dependent on, or it also depends on the objective that we are trying to optimize. So I'll move to the next one. So I mean, it's also something similar to what we discussed just now. So how do we optimize these other policies of hybrid storage systems using RL, and what are the challenges there? I guess we kind of discussed a lot on this. So data placement, eviction, and promotion have different actions. They also need different rewards, all these policies. So how do we make these policies work harmoniously for the overall improvement of the HSS? Any idea? I mean, the previous slide was looking at like objectives in terms of energy efficiency and endurance, but What really affects those is these policies that we have in terms of data placement, data migration, all that. So any suggestions on that? How do we make them work together and then improve the performance or improve the energy efficiency? Yes.
I mean, I guess trying to use reinforcement learning for these different decisions that we talked about is probably very much possible.
Yes.
And doable, but the question then becomes how do you communicate to let's say two decisions that we have. I mean, this is quite a big problem because one, we have like this asynchronous training, right?
Yes.
So that at some point these two processes will need to make some communication with each other, which is quite difficult, or exchange the information in terms of like reward, whatever you call it. And on the other hand, if you say, okay, let's make a big system that controls everything, all like big decisions as we said, like a small decision, then we have a lot more training complexity because the whole system becomes more larger. And becomes, I guess, even getting perfect accuracy is difficult because there's so many decisions to choose from, and you don't solve the problem of having like additional storage overhead or even having like additional training overhead. So I'm not totally sure what would be the best way. I obviously like major challenges.
Yes, and I should admit that these are all open-ended questions which don't really have a clear answer. So, any comments from you? Okay. So yeah, you're right. I mean, you can look at using reinforcement learning for each of these policies and then try to optimize that. But there is a challenge, as you said, is one is communication between these agents, or you could have an arbitrator at the top which looks at all these agents and determines which one should be more aggressive, which one needs to be less aggressive, establish a communication between these two things. So all these are design aspects that we need to take care in implementation, but it's a good uh, it's I think mostly in the right direction that anyone would think of in terms of optimizing all these policies concurrent in a parallel manner. So the idea is, as you said, is coordination. The key challenge here is coordination between the agents, and we could think of perhaps coordinating using the reward functions itself if we don't have an arbitration agent at the top. Or we can also look at um like making the input features as part of this communication mechanism. So yeah, I mean it's again a thing that we can all discuss and debate on, but what really works for a system and what really works for some of these workloads is something that we should see. So the last discussion point that I have is, do you see any security vulnerabilities in these ML-based approaches? So, okay, I'll also try to give you a hint on what I was thinking. So how do we break these systems? How do we make these agents perform badly, perform poorly, and so if we all become malicious attackers, then how do we do that? What are the different ways to?
Someone can create like badly such that it gets stored in other areas based on malicious behavior. And what it is supposed to store.
So, but I mean, the user may not get control of the training phase of these agents, right? You treat this as a black box. So how do you kind of see when the training is happening and then try to attack? Yes.
So I was following another thing, and maybe that I could structure my, let's say, rights this way that I kind of can control, understand where my data that I want is placed in. And so I can have effects like, for instance, RowHammer or similar to that. And I simply exploiting that I know that, okay, not often we use data stored here, and if I access data frequently, it's stored in this partition, maybe something similar to that.
You are more or less in the right direction. So the idea um, is to cause these adversarial attacks to, as I said, maybe do denial of service for these applications. And how we can do is we can also execute these malicious workloads with completely different access patterns uh, and run it in parallel with the real workloads. And that can, I mean, there are a lot of moving parts in this kind of design as well. So you have the experience buffer, the training size and training batch size and so on. So you can actually kind of mislead the agent to think that, okay, these are the workloads which are more dominant, as you said sometime back. And it can train for these kind of workloads, and then the real workload gets lost in this, or it can make decisions which are not ideal for the real workloads. And this is a very I mean, broad understanding of of these kind of attacks, but I mean it's an ongoing area of research that people are looking at in the ML domain. But in these kind of in a system like Sibyl, I think it's quite easy to cause this denial of service by just running a workload which is always accessing the data frequently, trying to write more and more data and accessing it. So Sibyl can think that it's a data hot data and then can try to place it in the fast device. So this can also have serious implications on the performance and the storage device lifetimes. So yeah, I mean it's something that is worth pondering. How do we build these systems so that we are robust enough to not have these kind of vulnerabilities? Any solutions that you can think of? Yes, please.
If multiple, let's say, processes access the same storage system, you could say that, just assume in this sense, like many, let's assume the same DNS, you could say that every process just has a specific part of their access pattern is going into the training set. So not, I don't know if it makes sense, but only a small portion of the training sets training batch is from each process. So no process in itself can overwhelm the whole training batch with like this wrong access. But then, I mean, if the more processes you have the same problem, but still kind of it's problem.
Yeah, I mean, there are actually some techniques that, I mean, I think I need to wrap it up quickly also, but there are some techniques that like gradient masking and this proximal policy optimization that look at um, basically improving the training stability and limiting the amount of changes that you make to the policy with each training epoch. But I mean, it's not clearly a good solution because this way you also make inaccurate decisions, or your policy doesn't really adapt to real workloads which have a very large variation in terms of access patterns. So yeah, and these are some techniques that we could explore and make it more robust. But again, it's not something that can work in other workloads where there are large variations. So I think I should wrap it up quickly. I've taken more than my share of time. So that marks the end of the presentation, and thank you all for participating in this discussion.
I'm not going to do the I can go. It's already done.
Oh. Okay.
Could you please turn to this? Yeah. Okay, thanks.
Okay, so let's quickly go through. I think we have a half an hour kind of time, so I'm not going to make you wait for more than what's required, but let's see. So yeah, this kind of synergistic with Rakesh, what Rakesh is talking about, like using machine learning in the computer architecture, but a different side of the answer. So we are going to primarily talk about the memory latency problem. So this is, I don't know whether you have taken the course on computer architecture or any related course, but this is a very typical chart that we normally see. So you can see three lines, right? So one is the memory capacity, bandwidth, and the latency. So what the line says that if you look into last 20, 30 years, right, so it almost that, your capacity has significantly increased, your bandwidth has also significantly increased, but as compared to the bandwidth and the capacity, latency has not increased much. So basically what it makes that if you look into modern workloads that puts a heavy demand on the data that it generates and data that it churns out, right? So they actually are more and more memory latency bound. Like the final memory is not kind of catching up with the rate at which it can be processed. So that's what the problem says, that long memory access latency eventually leads to the ultimate performance bottleneck. So we have techniques, primarily like three techniques: latency reduction, latency tolerance, and latency hiding techniques to make the processing faster as much as possible. There are some changes in the animations it seems. So latency reduction technique means it fundamentally reduces latency. Like for example, if you come up with instead of DRAM, if you come up with something more advanced, like for example SRAM, that is faster memory than what the DRAM can provide. So that's the fundamental approach. Also, you can go for data-centric approach. Like let's say instead of pulling the data from where it resides and then pulling it to the computational unit and then operate on that data, you can also go for data-centric approach, saying that okay, I'm going to offload the computation over there. So that's kind of also reduces the latency of the memory request, because you don't have to access the memory and then send it back to the compute unit. And then we have the latency hiding techniques, which is again like processor-centric approach. Typical examples being caching, prefetching, and then we have other techniques called like the latency tolerant techniques. So it's neither going to reduce the latency, it's not going to hide the latency also, but it somehow makes the processor more tolerable towards the latency. How tolerable? Let's say you can use let's say multi-threading. Right? So when your one thread is basically waiting on some memory request to come back, the other thread can actually go on that same time. So that's multi-threading, out of order execution, run-ahead execution. All of these basically fundamentally lies on this third class. Now, we have like, if you want to go through this, there are lots of lectures out there on the computer architecture as well as PDCA courses. So if you're interested, definitely go through them. So for today's discussion, I'm going to discuss about a technique which is fundamentally latency hiding technique, but it's not similar to prefetching. It has differences, also has some similarity towards prefetching. So it's kind of, let's say, of its own genre, kind of. So with that, let's talk about this paper. We have presented this paper in last year micro. It's called Hermes, accelerating long latency load requests via Perceptron-Based object load prediction. And as you can, as you can probably see somewhat that, okay, you were trying to go some speculation on the load prediction, let's say off-chip load prediction. I'm going to explain what does that mean. And then that prediction essentially going to hide some long latency from the processor's perspective. So the key problem that we are looking at here is that, the longer the memory access latency, the problem stems from there, that those memory requests, they often stall the instruction retirement from, there is a buffer in the processor, in the out of order processor. I'm not sure whether you have taken the course on computer architecture, but if you have taken, then you know this buffer, which is called reorder buffer. It's essentially a buffer that holds all the in-flight instructions, and you can execute any instruction from that buffer as long as they satisfy some conditions, right? But then if you have any long latency instruction out there, which is mostly like it's a long latency memory instruction, right? Then they often stall the processor by blocking this instruction retirement from the ROB, which essentially creates the performance limitation. Okay, so last like 30-40 years, we have invested a lot of research to reduce this sort of latency of those memory instructions. Okay, so the more latency that you can reduce, the faster you can process this instruction, the faster you can let the instruction commit, and hence the performance. Now, traditional solutions mostly lie on two different aspects, like what I just mentioned in the past couple of slides, right? That either we deploy, let's say, sophisticated prefetches, which, as the name suggests, prefetching means it's going to predict which requests are going to be accessed by the program next, and it's going to proactively fetch those data from the memory to the on-chip caches, so that when the program essentially trying to demand it, it would already find it in the faster on-chip cache. So that's what the prefetcher does. And then on synergy with this prefetching, we also have kept on increasing the size of the cache. Why? Because the more the local cache size that you are going to have, the more likely that any request is going to be coming out from the cache rather than you have to access the slower memory. So that's the idea, right? But then this actually has some problems. So that's what I'm going to discuss next. So what in this work, what we are observing is, the first observation is that even if you have a very state-of-the-art cutting-edge prefetcher deploy, right, you would see that 50% of the load requests that would go to DRAM, let's say missing the cache hierarchy and going to the DRAM, 50% of them can be successfully predicted by a prefetcher, but the remaining 50% would keep on going to the main memory. So you cannot hide them. So essentially, it basically says that whatever prefetching algorithm that we have, the pattern matching algorithm that we have, they have headrooms left, right? And if you look into this remaining 50%, then 70% of that 50% are the ones that are still blocking the reorder buffer. So basically, this dark red section is the one that are highly culprit for the performance limitation. Okay. Now, if you look into that remaining 50% that are still going to off-chip, what we are seeing that the way that your main memory or the DRAM is accessed is the following way, right? So you access the L1 cache, you access L2, you access LNC, and then you have access main memory. But now, in current processors, you have so big of this on-chip caches that L2, L1, sorry, the L2 or LNC access latency by itself has actually become a long latency. So what we observe in this case is that if you know that it's going, certain memory request is not present in the on-chip cache hierarchy, it would go to off-chip, right? It would go to the main memory. If you simply start accessing the main memory as soon as you know that it's going to be accessed for going to the main memory, you can actually save a lot of cycles. So in this case, what we saw that 40% of the stall cycles that are caused by these memory accesses that are still going to off-chip, they can be eliminated. 40% of that stall cycle can be eliminated if you just simply take this on-chip cache access latency from the critical path, so that whatever is left is basically at very beginning you would predict whether it's going to be going to the main memory or not. If it is, then you are going to access the main memory. So that's the key idea. Now, so this is another motivational data that this previous work has collected, and this is back in 2007. So as you can see on the right left hand side, it shows that from that 30 years, your cache size has been increasing a lot, and the heat latency of that cache is also increasing a lot. So it basically says that this trend in increase in cache latency is not actually stabilizing anything. The more we were going to go on the pursuit of increasing the cache sizes, the more this problem is going to haunt us. And it seems like this is still valid in today's time. And when the funny thing is that when we are actually conducting this research, the Golden Co, Intel Golden Co back in 2021 used to be the state of the art at that time. By the time we are presenting this research, a new processor code came up that's called Raptor, and within one generation, you can see your L2 size has increased, and so you have also added another cycle of latency. So it basically says that every new generation of processor with newer generation of processor, you are likely going to see the same trend going on for in the future. So that basically brings us to the goal of this work. That the goal here is that we are planning or we are targeting to improve the processor performance by removing this ever increasing on-chip cache access latency from the critical path of the off-chip load. So towards this, we design Hermes. So Hermes has two key ideas. So it's going to predict which load requests are likely to go off-chip, and for that particular off-chip loads, it's going to start fetching the data directly from the main memory while also concurrently accessing the cache hierarchy. And so Hermes employs the first for this off-chip prediction. It employs the first perceptron-based off-chip load predictor that predicts which loads are likely going to go off-chip by simply learning from the multiple program context information. So I'm going to give you a very brief overview of how Hermes looks like, right? So this is a traditional processor core. So you have the core, and then you have L1 data cache followed by L2 data cache, then LLC, then you have a memory controller which is interfacing with the off-chip memory. Okay. So now in the baseline, what happens is that you are going to access L1D, L2, LLC, and the off-chip memory, sequentially one by one, right? And if your processor has this latency tolerant limit, then for the remaining number of cycles, your processor is simply stalling. So you don't have enough parallelism left in the processor that can be utilized by that, for that time. Now, what Hermes does is basically it employs a off-chip load predictor, which we call named Puppet. So when the core actually generates a load request, at that time itself, it's going to ask Puppet, oh, is it likely going to go off-chip? If yes, then if Puppet says yes, then what Hermes does is it's going to access the L1 data cache. Why? Because you need the physical address to access this main memory, which happens in parallel with the L1 data cache access. So it's going to wait for the L1 data cache access to complete, and then once you have the physical address with you, it would issue a memory request directly to the memory controller, which would go to the main memory. Now consider this, that while it's accessing the main memory, the actual request is already flowing through the pipeline, right? If the prediction is correct, then it would eventually come back to the memory controller. At that time, hopefully, memory controller would say that, okay, I have already initiated this memory request from the main memory. So let's wait for that request to come back. Once it gets back the data, the memory controller would simply forward the data to the core. So if you do this, then it's essentially happening that your L2 and LLC access latency is actually getting hidden under the memory latency, right? So that in that way, even if your processor is stalling for that, the same amount of latency tolerance, but still you can save some stall cycles, which is basically improving the performance. Okay, is there anything Not understandable here? Okay. So then let's go to the now if you understand this part, then the protocol seems to be understandable. Then whatever is left is how we are going to design the object load predictor, because that's everything that kind of let's say acts as the brain of this proposal, right? So now let's try to understand how to design that object load predictor. So notice that this is not the first work to even envision this kind of prediction, right? So there are prior works that has, kind of laid out the groundwork. So these are the two specific type of, let's say, prediction mechanism that we can evaluate. So one is called the history-based load prediction, which is evaluated in HMP. It's not actually evaluated in this context, it was evaluated for a different context for instruction scheduling, but we can actually let's say repurpose HMP for our purpose. Okay, so that's the history-based prediction mechanism, and then we also have the tracking-based mechanism, which just simply tracks which cache blocks are present in the cache arrays. Okay, so history-based prediction uses a branch predictor-like structure, and then tracking-based mechanism, they also have some problems. So the problem is that you require a large amount of metadata for this sort of tracking, right? And the bigger the cache sizes are going, your metadata size is also increased. So it's basically you are trying to, let's say you reformulated that same problem into a different aspect, but the core of that problem stays the same. That if your cache size is increasing, then metadata would also increase, right? And then on top of that, you also need to track all the cache operations like evictions and then it also changes with the inclusivity bypassing mechanisms and so on and so forth. So it basically makes the entire proposal more complex. So on as compared to this one, what we are going to do in this work is we are simply going to have some we are basically going in a different path of saying that okay, which load is going to go off chip. It can be learned from the program features itself. Okay, and that's the whole idea here, that if you go for the feature learning mechanism, then you can go for a low storage overhead solution, as well as which provides the same accuracy with a lower design complexity. Okay, so yeah, so let's see how we are exactly going to do this. So we are going we designed the perceptron-based object load predictor based on a multi-feature hash perceptron model. So this sort of model, they have been developed and evaluated extensively in the context of branch prediction, but we are going to show that okay, you can repurpose these sort of models for object load prediction also. So how the model works? So you have, let's say, different program features extracted from the load request, and then what you're going to do is you're going to use this feature hashing. Okay, sorry. So let's see how the prediction happens. So for each feature, you're going to extract this feature from the load request, and then you're going to use some hash function to get a hash value of this feature. Use that hash value to look up into the weight table and get some weights for all these features. Once you get all the weights from these tables, you're going to sum up these feature values. So let's say, for example, your first feature has a weight of -4. -4 means it basically is showing that okay, if your prediction output is, let's say, given this feature, it's going to be off chip. So minus means that it's saying that negatively correlated, means if you have this feature, it's not going to be off chip, let's say with a strong confidence. If you have a positive value, means if you have this feature value, then it's going to be off chip with a very strong positive confidence. Okay. So what we are going to do in the first stage, we are going to extract all the weight values, just simply sum it up. Whatever is your sum, then you are going to use some activation. Activation is just as simple as, let's say, is it higher than some predefined threshold, like -2? In this case, okay, 3 is higher than the predefined threshold, then perceptron is going to predict that it's likely going to go off. Now let's say, if in reality, let's say this load request for which you have extracted these features and then made that prediction, let's say in reality it didn't go off chip. So what happens then? So you need to train this predictor also in that case, right? So how your training happens? So let's say if you don't have the load to be going off chip, so it means that your activation should not have happened. That means the sum of the weights, whatever you have got, it should have been actually lower than the activation threshold. So you need to detrain your predictor. So that basically says that okay, your sum of the weights should be lower than the activation threshold, which means you look up the predictor tables again with the same features and simply decrement all the weights. So if you decrement all of them, so it's basically going towards that direction. And oh, next time when I'm going to see the same feature, hopefully it's going to have a lower weights, which would be added up to a lower value, which would reduce which won't be finally activating the final output. So that's the idea. The same is also true if you get a positive reinforcement, right? Then you're going to say that, okay, I'm going to increase the value. So it's basically either going upwards or downwards. So the whole point is that if you can do, the training using a very simple increment and decrement operation, you don't need any fancy, floating point arithmetic, multiplication, and additions and so on and so forth. Okay. So we evaluate this idea on chancing trace-driven simulator using a wide range of traces, and we have also evaluated against large number of LLC prefetchers as well as object prediction techniques, and we have certain considerations regarding the latencies that we are using in for this evaluation. So let me quickly go through the performance numbers. So this is what PTI here is actually a prefetching technique, and then Hermes here is a object load prediction technique that we're discussing. So the first key observation here is that if you have like an object load predictor like Hermes, it nearly provides more than half of the performance benefit of a full-blown prefetcher like PTI. Now, so basically what it says that even if it provides almost half of the performance benefit, it still only consumes 1/5 of the storage overhead of what PTI does. So at per storage basis, Hermes still provides better, higher performance benefit than what PTI does. Okay, it's a full blown, and PTI, if you don't know, PTI is basically like a kind of, let's say, more complex reinforcement learning based prefetcher, which is like essentially what Rakesh was saying, right? So reinforcement learning, it's used in this context in PTI. Now, the second key observation is that if you include both Hermes and PTR on top of each other, you can literally do it. Like your system has like prefetcher as well as your object load prediction is going on. If you add both of them on top of each other, you are getting 5.4% more performance benefit on top of what PTR alone can provide. So that essentially shows that these performance benefits are let's say additive on top of each other. And the third observation is that if you have an idealistic version of Hermes, which essentially knows which load requests are going to go off chip perfectly, so our online realistic version of Hermes is providing nearly 90% of the performance benefit of what ideal Hermes can provide. So that also shows that your accuracy, your prediction is near to what you can also provide in the idealistic world. Okay. So I'm not going to, okay, maybe I can quickly show this one. Now, so this is one side of the performance side, right? So now what happens in the, let's say, increase in the main memory? So why this is important? Let's say if you have a inaccurate prediction, inaccurate object prediction, it means that inaccurate in the sense, let's say the predictor said that, okay, it's likely going to go off chip, but in reality it should not, right? So but what Hermes would do, it would just simply say that, oh, the predictor has said it's going to go off chip, then I'm going to access the DRAM. But in reality, you should not have access to the DRAM. So you may see that if you enable Hermes, then it actually increases the DRAM transactions. And the more DRAM transactions that you're going to see, the more power and the energy efficient, like energy dissipation you're going to see from the system. Okay, so that's why it's actually important to also see what is the percentage increase in the memory request as compared to all of the other prior techniques, right? So what you can see here is that if you have only Hermes, that increases the main memory transaction by 7.7%, I think, oh no, 5.5%. If you have PTR, then it increases the main memory transaction by 38.5%. If you add both on top of each other, it additionally, increases this main memory transaction by 5.9% on average. Now, the good part is that if you simply compare these numbers with the performance number that I'm showing over there in the offset, right? The performance number that you saw in the last slide, right? It basically shows that for 11.5% performance benefit over the baseline, basically the y-axis is normalized to the same baseline in both the cases, right? So for 11.5% performance benefit, you are only increasing it by 5.5%. For 20.3% performance benefit, you are increasing it by 38.5%. So what it essentially shows that for every 1%, for every unit performance benefit that the Hermes provides, PK actually provides it for 2% increase in the memory request. If you have Hermes on top of PK, then it needs 1%, it increases by 1%. If you have Hermes alone, then it only increases by 0.5%. So it basically says that in case your DRAM bandwidth is already very limited, which is typically the case for, let's say, large scale server processes, right? Like lots of computations are going on in every core, and you don't have enough ample bandwidth remaining. So in those cases, Hermes would actually be a better alternative for prefetching to improve performance, right? So yeah, so that's the key takeaway here, that it's more bandwidth efficient than the previous prefetches. I'm going to skip through these results, but essentially it shows that it doesn't, these benefits are not just simply on top of PITIA as a prefetcher, but if you have any other type of prefetcher, like in this work we have like evaluated so many other types of prefetcher, Bingo, SPT, and log SNS. Like there are so many prior works, and Hermes can actually provide performance benefit consistently across the entire scale. And all of this is just simply 4 KB of storage overhead, 1.5% of power overhead on top of systems. So there are lots of other data which I'm not going to cover in this presentation. If you're interested, definitely take a look at the paper itself, and there are other more in the extended version which is in the archive. So definitely check on the archive version. So basically to summarize, Hermes advocates for off-chip load prediction. As I said, like this is a fundamentally different form of speculation as compared to the load address prediction, which is employed by the prefetching. So it's kind of a new latency hiding technique as compared to what prefetcher does. But in the end, both of them actually hides the latency. Okay, and off-chip and what we show that off-chip load prediction can be applied either by itself, or it can be combined with the load address prediction to provide performance benefit on the system. And Hermes employs a first perceptron-based off-chip load predictor that has decently high accuracy. It's not that, it's not extremely high. It's not on more than 95% or so, but it has decently high accuracy, decently high coverage of load prediction with lower storage overhead, and then it provides high performance benefit as well as high performance benefit per bandwidth. That's what I mentioned. If you're interested, definitely it's open source, and if you want to, let's say, attack on this part, right? That okay, I want to make more accurate predictions and improve the accuracy, then definitely extend the code that we have, and it's like you can get all sorts of predictors, features out of the box. You can just go through the code, and you can easily have your own let's say predicted, and you can get statistics like false positive, true positive, false negative, all of this from pretty much out of the box. So yeah, so that's more or less of the presentation. I think I'm going to take like a couple of more minutes. So so the strength of the paper is it's easy to implement, much easier than the more complex let's say prefetching mechanisms. It requires minimal changes to the overall protocol also, like the figure that we showed, right, that how Hermes is injecting the memory request. The best part is that this prediction is not reactive, in a sense that even if you have a wrong prediction, at very worst, you are going to access DRAM when you should not have access to it. But it does not hamper your correctness of the program execution in any way. Like for example, if you consider the branch prediction, or let's say if you consider the value prediction, right? So they are reactive in a sense that if you predict something wrong, then you may need to roll back your execution. But in this case, it does not require any rollback mechanism at all. It has low storage overhead as well as it's open source, so you can anyone can try it. But then it also has some major weakness. That the one that I just mentioned, right? That if you have a wrong off-chip prediction, the bad part is it's going to access DRAM more than what it should have in the baseline, right? So accessing DRAM for more time essentially increases the DRAM bandwidth, which may have like very drastically wrong consequences if your DRAM bandwidth is already limited in systems, and also it increases the system power in general. So that's the major weakness. The second major weakness is that you can think of systems where you have off-chip load prediction on par with the prefetchers, right? The off-chip load predictor that we saw in Puppet in this work, right? It's actually aware of the prefetchers that are there in the system. So it knows that there is another agent which is prefetching the work for you. Okay, so in some sense, those memory requests are eventually won't go to the main memory. Okay, but the other is not true. So the prefetcher actually does not know anything about whether you have a off-chip prediction mechanism in the system or not. So this sort of, let's say, uncoordinated, solution that is essentially tackling the same problem may have also consequences, which is, I kind of skipped through that figure, but if I go back quickly to this figure, so it's basically, that's what it's showing, that if you have PTR, if you have Hermes, and x-axis you have the different bandwidths. So on the more you go on the positive x-axis, it's more relaxed in terms of bandwidth. The more you go on the negative, x-axis on the left, it's actually getting more constrained. Like for example, this is a threadripper configuration which had like 64 core, 4 channel memory bandwidth, something like that. But what you can see here is that when the bandwidth gets very constrained, right? At some point, Hermes starts performing better than what the prefetcher would do, because it's basically harming the performance, right? But then if you add both of them on top of each other, right? So Pitya plus Hermes, it literally, the curve literally seems like Pitya, but in a higher, like a shifted version. But that should not be the case. When, let's say, Hermes is better than Pitya in performance, right? It should have been, let's say, following Hermes more rather than Pitya. But that's not what is happening. Okay, so that's a major weakness in this work as is, right? So yeah, so that's the weaknesses. Now I'm going to just have some discussion points. So the first discussion point that I have is the following thing, right? So it's a very let's say, it's not open-ended, but it's a question that you can think of. So the question, the fundamental principle that Hermes says, and I always keep questioning papers like this in general, right? So the paper, any paper is going to tell you or trying to sell you the main hypothesis. On the face value, that hypothesis makes sense, but if you start questioning that hypothesis itself, then you need to understand, okay, oh, is this hypothesis true? Is this hypothesis complete? So that's what we are going to do now. So the main hypothesis of this paper is that, oh, off-chip load request stalls the retirement of the instruction from the reorder buffer, and hence they are critical to performance. That's the hypothesis, right? So we are going to accelerate those off-chip load requests. But the question is that, is this statement complete? Is this the only, so think of it in this following way. Is this a sufficient condition or a necessary condition? Any idea? Or it's neither?
I'm not sure, but I mean, aren't there also cases where it's not on the critical path, so we can continue with something else that we said?
Okay. So you are basically saying that off-chip load request may not be on the critical path.
Yes.
Okay, yeah. So that means you're saying that it's not a necessary condition, right?
Yeah, I just say it might be that there are cases where I can do this off-chip load request simply by doing something different, and then as soon as I get the request, I can continue with the work.
Possible, yes, possible. So this is one answering to one aspect of the question, right? That okay, it's probably not necessary, right? Is it a sufficient condition also? Sufficient in the sense that for being critical, does it need to be always off chip?
Probably also can be this cache before where you then have to retire and wait for the traffic.
Exactly. So as it seems, right, that many on-chip cache on-chip memory requests, right, which are not going to go off-chip. So to answer your first question, most likely if it is going off-chip, it's going to be critical path. Why? Because your DRAM is working at very slower frequency than your core is running on. So if it's going to DRAM, most likely, I'm not saying that it's 100%, but most likely it's going to be on the critical part. But let's say even if that thing happens, let's say with 99 or 98% of the time, the reverse is not actually happening even in the 50% of the time. Let's say not always it's the case that everything that everything that hits on chip is not going to be on the critical path. That's also not the case. So lots of accesses that are hitting on chip cache, let's say for example large LLCs, right? And typically in today's systems you have huge LLCs, like on the orders of hundreds of megabytes. So in those cases you can legitimately have on-chip requests that can also stall requirements, so retirements. So can you think of Hermes in this case, given this insight?
I mean, instead of simply asking the either main memory or the first cache and the second and third, we can ask the LLC, then the first cache.
Perfect. So that basically says that if you're not going to, why don't we have a binary prediction, but let's say ternary or more class prediction type. So have a fine-grained access for categorization that okay, if it is also going to hit LLC, we are going to do something for those requests also, right? So there are two let's say ways of doing the same thing that you just mentioned. So either we can go on the first approach, which is let's say predict which load request is going to stall the RO. That's let's say I'm just repurposing this prediction, right? So you can also go for this prediction that at the very early in the pipeline, when you have seen that load request, you are going to predict whether it's likely going to stall the ROB or not. So this sort of prediction has been evaluated in this follow-up work, which also uses Hermes as a comparison point. And then the other one that you mentioned that okay, how about we design the puppet not as a single class binary perceptron, but let's say ternary or a multi-class perceptron. So that's the other one. We have some follow-up work going on here, but if you're interested, definitely think of this direction. So there is other discussion point which I'm kind of I'll keep it open-ended as much as possible. So Puppet's accuracy is definitely not ideal. So it's only 77% on average, which is fine, but still you get this point that okay, for every 23% of inaccurate predictions, so it's basically saying that okay, it's going to likely go off chip, but it actually doesn't go off chip. So that means you have those many memory requests kind of let's say extra on top of what the DRAM is supposed to provide anyway. Right? So if we can improve that accuracy, it actually improves the performance, or most importantly, it improves the power efficiency more than the performance. So we can think of let's say improving the accuracy by adding more features, like for example some prefetcher specific features. Oh, how the prefetcher is thinking, right? Let's say is prefetcher seeing this sort of pattern, then I'm going to also use that pattern for my prediction, right? So adding more prefetcher specific feature would help. And the other thing that we can also do is we can just simply think of, let's say we have only discussed about single layer perceptron, right? It's just one level of all the weights, you're going to add them up, you're going to do a let's say activation, right? But so that essentially means that your final prediction, we are representing the final prediction as a linear combination of the features output. But what if it is not linear? So can non-linearity add some benefits on top of this? So that's the second thing that we can also do. So the third discussion point that I have is exactly the problem that I was talking about, that now we have two, let's say, two classes of solutions that are both hiding the memory access latency. One is prefetching, one is off-chip prediction. Now, how exactly you're going to co-optimize them? So off-chip predictor and prefetching, they should talk to each other. but how exactly you're going to optimize this? Any idea? Okay, if not, I'm just going to give you like a brief like solution. It might not be the best solution obviously out there, but let's say for example, you can just simply have a adaptive, let's say heuristic based adaptive technique. So you can say, oh, I'm going to, let's say, have a control mechanism that are going to say, oh, I'm going to either enable off-chip prediction or enable the prefetching or enable both of them or disable both of them, right, based on some feedback. Let's say you can think of it like, oh, if is your system's bandwidth is highly like extremely limited, is that so? If that's the case, then okay, let's have the off-chip prediction with a very high activation threshold, right? So that whenever you the prediction is going on, the prediction would be extremely accurate. But if we see that okay, it's a moderately high bandwidth consumption, not extremely high, right? Then we can say that oh, I can let off-chip prediction go with some normal activation thresholds. You don't have to be extremely accurate for that, but you can go through. But why we are selectively disbanding PTR from here or any prefetcher from here? Because prefetchers, as we have shown, right, they have more, they can provide more performance, but they also, for that performance, they are also going to consume a lot more bandwidth. So if bandwidth is something that is extremely constrained for your system, then definitely first turn off the prefetcher and operate on the off-chip prediction with some property, right? And but if you see that okay, my system bandwidth consumption is either medium or low, then you can just simply enable both the prefetching and the off-chip prediction. This is just a dynamic system, right? You can always think of, let's say, RL-based techniques that handle both of these things together. But yeah, that's there is possibility on that also. So with that, I think I would conclude it here. If we have any other question, then I can take it. Otherwise, we can just wrap the meeting. You have anything? Okay, then let's wrap it up here, and we will meet again in the next week. Thank you. Sorry? Okay, the next one.
Actually, suddenly is one of your scholars.
Yeah, we go for presenting this 2 weeks.
Have you contacted